Okay, we are on page 264 in your workbook, section 11.1. This is pretty much where we left off at the end of last semester. So the way this will work really is that I'm going to work through this just like we did in class last semester. The advantage with a video is if you want to hit pause to work through some stuff on your own and then hit play so you can check yourself, you can do that. You can rewind if you don't quite get something. So I think this will end up working out pretty well. Okay, this is interactions between atoms and molecules. We have looked at some of this before. Some of it will be also new. Strong interactions between atoms are called covalent bonds. We've learned this already. And those cause molecules to form. Remember, covalent bonds are between two or more nonmetals. Electrostatic attractive forces between ions cause ionic bonds to form, usually between a metal and a nonmetal. Weaker interactions between atoms and molecules are called non-covalent interactions. These cause gases to condense and form liquids and solids. These non-covalent interactions are also important in reactions involving enzymes and the function of nucleic acids, in the structure of your DNA that is essential to you existing, and in determining the structure of proteins, which again is what makes your body mostly. The properties of liquids, solids, and solutions depend upon the nature and strength of the non-covalent interactions between their component molecules. With an understanding of the types of interactions between atoms, ions, and molecules and their relative strengths, you can predict the physical properties of many materials and solutions. Okay, atoms and molecules interact with each other due to the interaction between opposite charges and the repulsion between like charges. Remember, opposites attract, like charges repel. Attractive interactions lead to the formation of molecules, liquids, and solids. So when different molecules and atoms want to be stuck together, that's when we end up with things like liquids and solids. When a solid melts or a liquid boils upon being heated, the molecules will acquire sufficient energy to overcome the attractive non-covalent forces, the stickiness of the molecules basically, and move away from one another. There is not enough energy, however, to overcome the covalent forces and break the bonds that will hold the molecule together. So the molecules stay intact, they just are no longer clustered together as closely. Interactions between atoms and molecules are given different names depending upon the characteristics or structural features of the atoms and molecules involved. The names are covalent bonding, ionic, London dispersion, hydrogen bonding, and dipole-dipole. Okay, covalent bonding interactions between atoms hold molecules together. We've learned about these already. These bonds are caused by atoms sharing electrons. Covalent bonds are strong, and it requires considerable energy to separate the atoms involved. Usually we show a covalent bond by drawing a Lewis structure. Right, something that looks like this. Right here, these are the covalent bonds. They attach those hydrogens to that central oxygen. Ionic interactions result when electrons are not shared by atoms, but are transferred from one atom to another. Okay, we've learned about this already before too. For instance, we have sodium that has originally one valence electron, chlorine has 7, but this electron goes to join the chlorine, so we end up with something that looks like this, where chloride now has an octet. So this positive is attracted to this negative. That's ionic. So positives and negatives are kind of attracted to one another. Okay, so we've learned those. London dispersion interactions, these are new, occur in all substances. They result from fluctuations in charge distributions that cause one part of an atom or molecule to be momentarily positively charged and another part to be momentarily negatively charged. These instantaneous fluctuation means that they're just for a short time, and fluctuation means that they kind of come and go. They're not steady. They result in attractive interactions. The non-covalent interactions between atoms and or nonpolar molecules result only from London dispersion interactions caused by these fluctuations. So with these, I kind of think of this as like a bucket of water. So here's our bucket, and you're carrying it with a handle, and as you carry it, the water kind of sloshes around in here. So this would be kind of the negative side, this might be more of the positive side, but when you take another step, it could be that your water sloshes like this. So think of London dispersion interactions like water sloshing in a bucket. It fluctuates, it's momentary, and it changes from moment to moment. Okay, hydrogen bonding. Well, let's do some highlighting here. London dispersions, they occur in all things. The non-covalent interactions between atoms or nonpolar molecules result only from the London dispersion forces. So they are instantaneous, and they are weak. In hydrogen bonding, a hydrogen atom bonded to one of the small electronegative atoms. Okay, we need to highlight this. Oxygen, nitrogen, or fluorine has a slight positive charge, is attracted to the electrons in another one of these electronegative atoms. So for hydrogen bonding, you need a hydrogen on an oxygen, nitrogen, or fluorine, and that's going to be attracted to a oxygen, nitrogen, or fluorine lone pair. Okay, we'll see that, an example of that here in a little bit. So you have to have a hydrogen on an oxygen, a nitrogen, or fluorine. That hydrogen is then attracted to another oxygen, nitrogen, or fluorine, the lone pair on that. Dipole-dipole interactions are the interactions between permanent dipoles. So this up here, this we can kind of think of as dipoles, where we have a negative side and a positive side. However, the ones that I drew up here in the bucket, that's instantaneous, it's not constant. Dipole-dipole interactions are between permanent dipoles. So for instance, if you have a molecule like this, we did a little bit of this at the end of the last semester. The oxygen is more electronegative. The carbon down here, remember this is a carbon, is a little more positive. So this right here, this would be a permanent dipole because the oxygen's more negative, the carbon's more positive. As a result, the electronegative end of the molecule attracts electrons and has a slightly negative charge, which we showed right there. The opposite end has a slight positive charge down here because it's had some of its electron density pulled away from it by that oxygen. The dipoles in different molecules attract each other when the positive region of one molecule is close to the negative region of another. Remember, opposites attract. The dipoles repel each other when charges are close together, when like charges are close together. Hydrogen bonding is a type of dipole-dipole interaction that is especially strong and localized to a specific atom involved. Okay. If you need to do some more reading on that, check out section 11.1 in your textbook. It goes much more in depth. You can also check out section 8.4 in your textbook for electronegativity. That's on page 338 or so. Actually starting on page 336. 336 to 340. Okay, if you need more help, you can check those out, or you can ask me. Okay, here in Model 1, we have a table where we have our different types of interactions that correlates the type of electrostatic properties of atoms, ions, and molecules with the attractive non-covalent interactions between oppositely charged particles that result from these properties. The strength of the attractive forces is greatest in the top left corner, so this is where we are strongest, and it is weakest in the bottom right. Okay, examples are provided for each type of interaction. Let's take a look at one of them. How about this one right here? So the dipole-dipole interaction, in this one, we have the iodine in iodine monofluoride is attracted to the fluoride in iodine fluoride. So this bond kind of makes it look like the bond or the attraction is between two fluorines. Maybe a better way to draw that would have been something like this. Okay, the interaction is between the iodine and the fluoride. So that same scheme is used throughout the rest of this table. Okay, flipping to the next page. Sorry, you're going to have to flip back and forth a little bit. The table includes interactions between atoms and ions and molecules of pure substances and mixtures. Where do you find the interactions of pure substances on the table? So, we're going to look for interactions between two things that are identical. So, for instance, I see hydrogen between H2O and H2O. Okay, so that would be in a pure substance. The one below it, we have the hydrogen in H2O and the fluoride in IF. That would be a mixture because it's not between two of the same thing. Okay, the other place we see, here's two identical ones, IF and IF. Here's Br2 and Br2. And we can look anywhere else in the table, like IF and Cl. That's not a pure, that's a mixture. H2O and IF, H2O and Br2. This is between two different things. So we see our pure substances on that diagonal. The diagonal from the top left to the bottom right. So interactions for pure substances are found along the diagonal from ionic bonds to the London dispersion forces. So that's the top left to bottom right. Okay, the nice thing about video is if you need more time to write stuff down, you can hit pause, like right now. Okay, what is the strongest non-covalent attraction? What is the weakest? So, looking up here, we labeled this already. Let me get rid of some of this other writing here. We read that the strongest ones, the strength of the attractive forces is greatest in the top left, weakest in the bottom right. So the strongest is ionic bonds. Okay, then the weakest, if we check the bottom right, is London dispersion forces. What information is required to evaluate the strength of non-covalent interactions? Okay, so on this table, the electrostatic characteristics of substances outlined on the table are necessary to be able to evaluate the interactions between them. So, all of this information contained here. So, whether we have a hydrogen atom capable of hydrogen bonding, whether we have a polar molecule, whether we have an induced positive charge, that temporary dipole, those things are what we call the electrostatic characteristics. So the electrostatic characteristics of substances outlined on the table are necessary to be able to evaluate the interactions between the different substances, even if, depending, different substances if it's a mixture, same substances if they're pure. Okay, what is required for hydrogen bonding to occur between molecules? Okay, we talked about that. That's up here. So right up here is where we discuss hydrogen bonding. We can also see hydrogen bonding discussed, in the table. So if you need to, hit pause, try and answer this on your own, and then come back and check. So for hydrogen bonding to occur, we need H atoms, hydrogen atoms. They must be covalently bonded to one of three possible elements. So it needs to be a fluorine, oxygen, or nitrogen, and need a lone pair on a fluorine, oxygen, or nitrogen. So, for instance, you could have, I'll draw out an example of what we would need. Here's a Lewis structure for methanol. Okay, so we have a hydrogen attached to an oxygen, and then say we have, about ammonia. So both of these would count, but we're going to say right here, this is our hydrogen atom on the fluorine, the F or the N, okay? Over here, we have a lone pair on a nitrogen. So the hydrogen bond, maybe I should draw this a little bit differently. Let's see. Since it's not a full bond, I'm going to draw it as a squiggly line. This is our hydrogen bond right here. It's not a covalent bond, it's weak, it can be separated easily, but that specific interaction is met because we have a hydrogen attached to an oxygen, and we also have a lone pair on a nitrogen. Those fit these characteristics, these requirements above. Okay, moving on. Here's a table where we have something called dissociation energies. A measure of strength of an interaction between two atoms or molecules, it could be a bond, it could be just an interaction, is the energy required to separate them. It's kind of like the tug of war of atoms. The stronger the interaction, the more the two teams would have to pull in this tug of war. This energy is called dissociation energy. To associate means to come together. To dissociate means to separate. Dissociation energies for some interacting systems are given below. If it's a positive value, is shown as a energy required to separate. Repulsive, so we see the word repulsive here, would be meaning that they are already repelled by one another, so it's not going to take any energy to do that. So notice here also we have H2O, 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 HOH. Surprise, that's H2O also. It's just shown as HOH because they want to talk specifically about this bond between the oxygen and the hydrogen. So they have water in three different sort of alignments. Which system in the model involves a repulsive interaction? Okay, for each of these, I think it's good for you to take some time to try to figure out the answers on your own. So whenever I read a question, please hit pause, take a second to go answer it, and then come back and check yourself. You don't even have to write it down, but you can answer things in your head and then check before you do write it down. Okay, so which system in the model involves a repulsive interaction? There's only one, and it would be two H2Os, two waters, with parallel dipoles. Okay, so that means, if we compare anti-parallel, notice how these gray things, those are the hydrogens. For parallel, they're lined up perfectly. We have the hydrogens are behind the oxygen in both parts. So the hydrogens are the more positive part, they're lined up together, and the oxygens, which are the more negative part, are lined up together. And remember what we said, that like charges repel. So that's why, the positive parts are put together, the negative parts are put together, so they're going to push away. The anti-parallel are not that way. The positive parts of the water are in the back side on this one, and over here they're in the front. So we don't have that perfectly lined up repulsion. Okay, which system has the weakest interactions according to its dissociation energy? So repulsive, but then weakest after that would be what we find right up here, the two neon molecules, or atoms. The weakest interaction equals two neon atoms. So they have the smallest dissociation energy, so that means it requires the smallest amount of energy to separate them. Of the systems in the model, which two have the strongest interactions? Okay, so I want you to hit pause and flip back here and answer which ones have the strongest interactions. Okay, we should say the second strongest one is this bond right here. And the next one would be the sodium chloride, because it's clear at the bottom. So these are the strongest. We could also note that because these are so strong, they are considered chemical bonds. Right, this one would be a covalent bond. It's between two nonmetals. Sodium chloride we should be able to recognize as ionic. As the value of the dissociation energy increases, more kinetic energy. Remember, kinetic energy is how quickly these atoms or molecules are moving or vibrating, which increases with temperature. So more kinetic energy is required to overcome the attractive forces between the particles. Which system in the model would you expect to have the lowest boiling point, and which would you expect to have the highest? So explain. So again, I want you to hit pause and take a moment to think, which of these do you think low dissociation energy is associated with low boiling point or high boiling point versus high dissociation energy down here? So again, take a moment to think and then come back for the answer. Okay, so the answer would be the lowest dissociation energy is neon, which would mean it has the lowest boiling point. Okay, the highest dissociation energy is the sodium chloride, which would mean it has the highest boiling point. Okay, the stronger these dissociation energies are, you can think of it as how sticky they are, right? Particles with a high dissociation energy are stuck to each other, they're sticky. For something to boil, we have to take atoms that are stuck together and we have to remove them and send them off alone by themselves. So the stickier they are, the harder it is to remove one of them and separate it from all the others, which means it would have a higher boiling point. So higher attractive forces, stronger attractive forces means stickier molecules, means higher boiling point. Question 8, why do you think more energy is required to separate two xenon atoms than is required to separate two neon atoms? Remember that electrical forces, which depend on the number and charges of the particles involved, are stronger than gravitational forces, which depend on the mass of the particles. So that last sentence is just saying the mass itself doesn't have anything to do with this. What else? And look at your periodic table, find neon is atomic number 10, xenon is number 54. How else would those two differ from each other, even though they're in the same column? So again, hit pause, take some time to think about it, and see if you can come up with an explanation. So one explanation, neon has 10 protons, while xenon has 54 protons. There's more to it. This is fairly simplistic, but because xenon has more protons, it has a larger Z effective. Do you remember that term from last semester? Z effective is that nuclear charge that pulls on the electrons around it and so on. So, stronger interactions thus higher dissociation energy. Right? The mass would increase with more protons, but it's that extra positive charge that xenon has in its nucleus versus the neon. Okay, why do you think that energy is required to separate two water molecules in an anti-parallel configuration, but in parallel configuration, water molecules repel each other? So we talked about this already. It has to do with how they're lined up. So this is maybe easier to show in a drawing versus in words. So hydrogen, oops, I drew this wrong. This is what water looks like. And we have these dipoles, these positive parts and these negative parts. So I'm just going to show this as plus, negative, plus. Okay, if we have two molecules, we're going to draw the purple one in front, and how about the back one is going to be in red. Okay, and this is kind of hiding back here behind. We're just going to make that one have a little bit longer of a leg. Okay, so our interaction is going to be between here and here and here. Right, so the purple one's in front, the red one is in behind. Okay, so that was in the parallel configuration. Okay, the anti-parallel was drawn more like this. So we have that, and then the anti-parallel is here behind. Okay, so here the interactions, there can exist interactions. These positive hydrogens can interact there, and something like this. So over here, what do we know about like charges? Like charges don't attract. However, positives are attracted to negatives, and that can exist in the anti-parallel. So this can be a little bit of a challenge to write in words and also to draw in pictures. But the essence of it is, in parallel, we have like charges lined up right next to each other. If we switch it to anti-parallel, if we turn one of those waters up on its head, then the positive side of the water is lined up to the negative side of the other water, and we have more attraction. Why do you think that water in a head-to-tail orientation has a higher dissociation as compared to the anti-parallel and the parallel orientations? Okay, so head to tail, let's look at that. So in head to tail, we're going to have something that looks kind of like this. So we have, let's draw these in colors. We're going to have positive B, or negative B, the oxygens, and the positive ends is going to be the hydrogens. So in the head-to-tail orientation, we can have this interaction right here between the very negative side and the more positive side of the water. And do you remember there's a special name for this type of interaction? A lone pair on an oxygen and a hydrogen bonded to an oxygen. you flip back a couple pages, you'll see that we have hydrogen bonding is possible here. Okay, so in head to tail orientation of water, we can have hydrogen bonding, which is a strong molecular attraction. And that's not possible with the, or as possible with the antiparallel and the parallel orientations. Okay, so what insight has your team obtained so far about why some substances are gases at room temperature while others are liquids or solids? Okay, this is another one where I'd like you to hit pause and see if you can think of some specific points why that is true. So hit pause, take a minute to think. Okay, so it boils down to this. Materials with strong interactions strong interactions, meaning the intermolecular attractions, are liquids or solids at room temp. And that being because the molecules stick to one another. Remember, strong intermolecular attractions means the molecules are sticky. And quite literally, when you spill a sugary drink on the floor and your shoes kind of stick to it when you walk by, it's because they're forming intermolecular attractions with the sugar, which is full of hydrogen bonding locations on the floor. So, quite literally, in the case of sugar water on the floor, it's sticky. Okay, but materials with weak intermolecular attractions are not very sticky and are easily separated and can become gases. Remember, gas particles are separated by great distances. Okay, oxygen and methanol have the same mass, 32 AMU. Explain why oxygen is a gas at room temperature and while methanol is a liquid at room temperature. Okay, hit pause again, see if you can come up with an explanation. It all has to do with what intermolecular forces they are capable of. Okay, O2 is only capable of London dispersion forces. You can check that table back on the second page of this activity and find they are weak. Methanol, CH3OH, we looked at that back down here. This one is methanol, and we decided that it was capable of hydrogen bonding. So methanol equals hydrogen bonding, which means it has strong intermolecular attractions. So strong intermolecular attractions equals more likely to be a liquid. Weak intermolecular attractions likely means that it's going to be a gas. If for some reason the two molecules chosen were both liquids, the one with the stronger intermolecular attractions, the higher dissociation energy would then have a higher boiling point. Okay, this exercise we're going to skip for now. I don't know that it's really all that useful. Basically, it's having you go back to here, and it's useful classifying each of these types of interactions based on whether they're London forces or hydrogen bonding or so on. So we can do a quick version of that. Go ahead and hit pause and see if you can answer them on your own, and then you can check yourself. So 2 neon, we get London dispersion force. 2 xenon, we get London dispersion. Right, 2 nonpolar things, when they're next to each other, they have London dispersion forces. 2 H2Os that are anti-parallel. Right, we looked at that on these questions just a few ago, like up here. So if they're anti-parallel, then we have dipole-dipole. Right, positive end next to a negative end. So that's attractive. Okay, 2 H2Os and parallel, they can be, we should write this as attractive. We also had dipole-dipole, but this one was repulsive. That's not how you spell repulsive. Right, if you have 2 positive dipoles next to each other, they're going to be repelled. If we have a positive dipole next to a negative dipole, they're going to be attractive. Okay, when we put them head to tail, then we got hydrogen bonding. That's nice and strong. In this case, we have the hydrogen that is actually bonded to the oxygen. That's covalent bonding. Right, that's not even intermolecular attraction, that's an actual bond. Okay, going on. We're going to do this one together, and then the next question is going to be your homework quiz that I'm going to have you upload to Moodle. The boiling points of butane, acetone, and propanol are 0 degrees, 56 degrees, and 97 degrees, respectively. These molecules, which are here, have about the same number of atoms and electrons and similar molar masses, yet their boiling points are very different. Identify the dominant non-covalent interactions present for each of these molecules and explain why these interactions cause their boiling points to be so different. Okay, so we're going to just label these as A, B, and C. In A, we can check back a couple pages ago, and we'll find the only intermolecular forces for this molecule are London dispersion forces. Checking on our table, London dispersion forces are down here. They're weak, and we know that weak intermolecular attractions mean low boiling point. I'm just going to call it IA. Intermolecular attraction equals low boiling point. Okay, B. When we look at this, we see an electronegative oxygen at the top and a much less electronegative carbon right here. So remember, this is a carbon. Every place where there's a zigzag. Okay, if you need a refresher on your electronegativities, find that on page 338. So electronegativity table is on page 338, and you can calculate those differences. We did that probably last November. Okay, so acetone, B has a permanent dipole. Because it has electronegativity differences between the O and the carbon, oxygen and the carbon. So that means it has stronger intermolecular attractions. permanent dipole is stronger than London dispersion forces. So that means not a stronger boiling point, a higher boiling point. Okay, and then C. So on this one, we have an oxygen with a hydrogen bonded to it. So thinking about the types of hydrogen bonding that we can, or the types of intermolecular attractions, hydrogen bonding is the strongest one. And for that, we need an oxygen, a nitrogen, or a fluorine, and one of those needs to have a hydrogen bonded to it. So we have propanol here. We have our hydrogen bonded to an oxygen. We also have an oxygen that has lone pairs. So that means this molecule can hydrogen bond to itself. So we have hydrogen bonding. Hydrogen bonding is a strong intermolecular attraction. Which means it's going to have the highest boiling point. So this trend for boiling points is easily predictable, so long as you know what your intermolecular attractions are. Okay, on this one, I would like you to do this for your quiz, not really a quiz, but I'd like you to work this out, take a picture of it, and upload it to Moodle. Okay, identify the most important type of non-covalent interaction for each of the following substances. Okay, here I want you to hit pause, and I want you to think these through, and then come back and check your answer. Okay, Ba barium sulfate, we're going to be ionic. Argon is going to be London dispersion. Right, it has no permanent dipoles, so it's limited to London dispersion forces. NO2, you might have to draw the Lewis structure for NO2 in order to be able to figure that one out, but it has dipole-dipole interactions. Notice it has lone pairs on nitrogen and oxygens, but there are no hydrogens around, so it cannot hydrogen bond. However, HF can. So we have hydrogen bonding with HF, hydrofluoric acid, or hydrogen fluoride. Okay. Which of the following does not form hydrogen bonds? Okay, again, I want you to hit pause and come back and check your answer. Oh, I skipped one. Well, we'll come back to that. Okay, the ones that does not form hydrogen bonds are this one does not. We have no hydrogen on an oxygen, a nitrogen, or a fluorine. And HCl. HCl is not bonded to, the hydrogen is not on an oxygen, a nitrogen, or a fluorine. Cl is right next to fluorine, so it's still probably a pretty strong interaction, but it is not technically a hydrogen bond. Okay, why these compounds have differing boiling points? We're not going to take the time right now to go through each of these. However, it's all going to boil down to the type of intermolecular attractions that each one is capable of. Okay. A few of these, we're not going to necessarily write these down just to save ourselves some time because this video is already getting a little bit long. Do you expect adding an electronegative atom to an alkane will increase or decrease its boiling point? An alkane is something that has just carbons and hydrogens. And the answer is adding an electronegative atom, such as a halogen, to something that's just carbon and hydrogen, so an alkane, is going to increase its boiling point because it's going to make it polar. So it's going to take a nonpolar element with only London dispersion. Adding a polar end to it will give you dipole-dipole interactions. So therefore its boiling point will increase. Why is the boiling point of ammonia higher than the boiling point of ethane? So here's ammonia. Ethane looks like this. So hopefully by now you're noticing right away we have a hydrogen attached to an oxygen-nitrogen or fluorine, and we have an oxygen-nitrogen or fluorine with a lone pair. Ammonia can hydrogen bond. This molecule, ethane, is nonpolar. It doesn't have lone pairs. It doesn't have a dipole, a permanent dipole. It has London dispersion forces. So ammonia, stronger intermolecular attractions, higher boiling point. Sodium chloride is an ionic compound. Ionic compound is the strongest of the attractions, therefore it has a high boiling point. What type of interaction is responsible for water's high boiling point? So again, water is capable of hydrogen bonding, which is a strong intermolecular attraction. Hydrogen bonded to an oxygen and an oxygen with a lone pair. So it can hydrogen bond to itself. Okay, that's that. That wraps us up with our intro to intermolecular attractions. This is a super important concept, especially if you go on in chemistry. This is like all of organic chemistry is based off pretty much these intermolecular attractions. So again, don't forget, I want you to do number 3 here. Work it out on some paper, take a picture, and upload it to Moodle, just so I can make sure that you guys are thinking along the right line of thought. All right, that's all for now. Be sure to check Moodle regularly to make sure you're not missing out on anything. I'll talk to you later.